spot on the melon.
There's a few spots on that melon.
Is that melon map related?
We were doing spherical coordinates in Calc 3. So you cut the melon along lines of constant latitude.
Oh, yeah.
And then constant longitude. And you find these little chunks that you eat when you get those, and they vary in size depending on where you are. So the point is to explain that in spherical coordinates, the volume element is r squared d sine phi dr d theta d phi. But would anyone like some melon?
Like,
Thank you. Seriously? It's a good time of the day for melon.
Get into the people.
You want to do the quiz? Okay, so let's do our...
do people want to do the quiz versus having melons?
I said people. I wanted to get into doing people. She said quiz. I just have a quick question.
Yes.
So for the quiz sake, for odd and even, we do this for that.
For what?
The odd and
Yeah. So like 3 is odd and 4 is even.
Oh wait, you're going too fast.
no. For the grid. That's nice.
For the grid.
Yeah.
So it won't necessarily be a grid. In that one problem, there was a grid.
Yeah.
So you just look at each point and count how many bridges are leaving it. Right? How many of those lines depart from that point. And is it an odd number or even number? That's the degree of the node.
Okay.
It's just counting the number of
If there's
outgoing
0 odd nodes, it's a circuit, and if there's 2 odd nodes, it's a path, and if there's anything else, it doesn't work.
You can have one odd. You can have one odd.
Try to draw one odd
So if there's
node.
exactly 2 odd,
You'll find one odd
Oh yeah.
If there's 4, you can't get to every dot.
can't, because then you have 3.
Well, what if I give it like a really bizarre hat?
I guess so.
That would be a very odd
Yeah,
that's why there has to be.
That one's not wearing an odd hat. Therefore, it's an odd node.
It's pretty odd. I agree.
Thank you. The term odd is not well defined.
Right. That one's right. But you don't have to go over it. You teach someone something.
Too far out.
Was that?
That's him.
That's what he was
Right.
saying. And I gotta say that rectangle prism one was hard just because I was having trouble following all the lines.
Yeah.
I was like, wait, no, did I go over that? No, maybe. I don't know.
You're having trouble following a 4-dimensional object in 2-dimensional space? For shame.
It's funny when you try to use one computer's mouse on a different computer.
Yeah.
But I got it.
Nice.
I had the most trouble with these two lines.
Oh,
These
yeah.
2 lines because the node, I'm like, did it?
Oh,
Oh,
yeah.
I went to that node. Wait, no, that's not the same line. Hold on.
That was a certain thing.
It is an appropriate time to play versus
So
music.
really, this week was only in path.
Okay.
That's good line.
What about the only factor?
Now.
So they're ordinary variants.
Yeah, you do.
Are there also both?
We're working now? Okay. Sorry. No, hold on. Is today really the 29th?
Today is Christmas, the 1st.
December.
December 1st. So the quiz we'll do in the last 10 minutes. I don't think it's going to take more than 10 minutes.
Yeah.
We're both going.
Yeah, I'll be right back.
excited.
I have to review first, and then we'll talk about George Cantor. Who's our next mathematician on that giant list?
He's actually more of a singer.
It's a different thing. Cantor means a singer, actually.
No.
It's, especially in the Jewish tradition. Maybe in Roman Catholic.
Also Catholic as well.
Oh my god.
So that leaves us with, after cancer, for next week, we have Sofia Kovalevskaya and Emmy Notter, probably, well, arguably the two most famous female mathematicians of all time. I think Sophie Germain is up there too. And then we'll end with a little bit of World War II history and Alan Turing. That'll be
And that heavy story.
sorry?
And that heavy story.
Well, it's a tragedy. That's where it is. In many ways. Did anybody see the movie The Imitation Game? Did I have a review of that? It's disturbing. So I said we were going to do review first. Good on that. Oh, I remember. I don't have my packet on the computer, so that's not good. So does anybody have the packet visible that you want to display on the overhead? Okay. So, thank you. And
I don't think I would appreciate my laptop.
up there. Let's adjust this so we can see the screen. Come back in a second. So the grid-looking thing here, we're asked, so that's obviously not Mechanicsburg anymore, but you can still ask the same question. Can you find a way to trace through there and end up covering all those bridges, all those edges once, and only once? And the problem is that there are some nodes on here that are odd. That one right there has 3 lines coming out of it. Now the problem for some people is they see this as a single line going through the point. Don't do that. Think about it. Starting here, how many routes away from here do I have? I can go that way, that way, or that way. So that's 3, but that's okay. You can have a Eulerian path if you've got an odd node. It has to start there or end there. But the problem for this guy is that there's that one, and that one, and that one, and that one. There's 4 different odd nodes on here. So we've got to start and end in 4 places. It's too much. If you use 2 of them for your start point and end points, you're going to still have some odd nodes that you'll encounter somewhere along your route. Figure out how that's going to work. You're going to come into that guy, and then you're going to leave it, and then you're going to come back to it. It's degree 3, and you're going to be stuck, and you won't be able to get to your eventual end. So, Vasana, you kind of summarized the setup for us. Maybe there's no odd nodes, in which case you can just draw it. Just try, and you'll be able to draw the Eulerian path, or circuit, I should say. If there's exactly 2 odd nodes, then use one for the start and one for the end, and try, and you'll get it. You can always do it. And if there's some other number of odd nodes, you can't have not a circuit nor a path. It just isn't going to work. Michael, you just asked the question, which is an insightful one. What if you had 1 odd node? Could you do that? So here's a weird way to approach this. This is literally a thinking outside the box moment. What do you get if you add up all the degrees on that thing? Every single degree you see. Why do you get an even number?
You have an even number of odd nodes and the other nodes are even, so.
Okay, so why do you have, what I'm getting at is why do you have an even number of odd nodes? If you add up, the degree here is 2, the degree here is 3, the degree here is 4, and so on, you just go all the way around this, you'll find that you've just counted all the edges twice, right? Because like this edge, it'll be included in this 2 that I count, but it'll also be included in this 2. The edge between these 2 nodes will be included. It'll be one of the things we count in that 3, but it'll also be one of the things that's counted in that 4. So by the time we go over the entire graph, we've added all the edges in twice. Definitely an even number for the sum of all the degrees. Any even degrees have no impact on the sum of the degrees in terms of its evenness or oddness. So how many odd nodes can there be? It has to be an even number. So you'll always have an even number of odd nodes in a graph. So that's a good little factor to remember. Anyway, for the purpose of this one, you say there can neither be a circuit nor a path, and it's because there are more than two odd nodes. I'm loving what you did there. So this is asking, is there a covariant circuit in a graph? It's a closed walk. Oh yeah, just reminding you what that was. Does this following graph have an covariant circuit? Yes, then indicated by numbering the edges. Oh, so I told you what to do. But that's a good way to go, right? If you want to show the path you're following, say here's edge 1 and then here's edge 2, and that way that you've crossed them off so you know not to recover them again, but you've crossed them off in a way that will let you know once you're done how you travel. So how did you travel this on? Looks like you started here. You went 1, 2, 3, 4. Boy, you got back to where you started. It's okay, I guess.
Still got another path.
You got another way out, don't you?
And it's down on the way.
5, 6, 7, 8, 9, 10, 11. I think my tendency is to try to go all the way around the outside and then plunge in and do the middle and then. But leave yourself awake. Basically, it's an exercise in thinking about and forethought, thinking about how am I going to get out of here once I get into a region. I leave myself an escape route and a way to get back to our initial point. I think you did a good job of that. Did most people get that one? The screens look good? Yeah, I thought it was maybe a bit too complicated, but it was. I mean, too many edges, but it's not so complicated. This one, on the other hand, is complicated. That's a Hamilton circuit. Now, again, how can I draw a Hamilton circuit so I can see it? Some edges of the graph will be in the circuit, and some edges will not be. So what she's done is doubled up the ones that are in it. She's also supplied a direction, which is pretty good too. She did a lot more back and forth between the cubes than I would have done. So she went over, moved around, and then came back, and then moved around in here, and went over, and then returned back. There's 4 of these. How many of these edges that go between the two chunks are there? So 1, 2, 3, 4, 5, 6. That's good, because it has to be an even number. Right? You're going to go over and return. What I would do, frankly, is make a Hamilton circuit on each one of these cubes separately, and then just join them together. Because you've got every possible edge that goes between the two cubes. But let me just say this. That's a great exercise for like homework. That wouldn't make a good quiz question because it's too involved. But if you've sat down and knocked through something like that for homework, then you're going to be fine. That's one of the questions. So I definitely like to distinguish between quizzable stuff and what's okay for homework.
It's not simple. It's not simple.
Do we have an Eulerian circuit or path on this final thing? I do want to point out one thing. There's a spot right there in the middle where 2 edges cross by each other. It's like wires going by one another. They're not touching. If you saw roads like this, it would be one on a bridge going over the other, or the other's in a tunnel going under the. So anyway, that's not a point where there's a connection. It's just 2 ships passing in the night. 1, 2, 3, 4, 5. I got an odd degree right there, and 1, 2, 3, 4, 5 there too. Those have to be our start and end. You didn't draw this one in for me.
I put a circle at the start and just said it was a path.
Oh, wait a minute.
You're just asking me if it's a circuit or a path.
Does
Didn't
it?
say do it.
Doesn't say do it, does it? Wow.
I was lazy. I just marked there's a cert, there's an end, and I circled
There's a
path.
path. Boom. I would like more explanation than that. It's a connected graph with exactly 2 odd nodes, so there is a path.
On a quiz, I did more explanation.
That was just okay. Do you want to actually try it? No, who cares? We know it can be done, right? I kind of agree with you here. You don't need to do it, but don't say it.
Can we do it though?
Sure. Let's see if I can do it. I want to start, say, at this one. How about we just go right on across, get all of those. Is that smart?
I went up and around.
How about we go up and then down? Is that smart? Why not? How about we take this big loop all around, and then we've got only one way out of there. And then I gotta go. Wow, I think I screwed with this.
It's still okay.
No, you're good, you're good.
It's still okay.
I gotta go up,
Go out.
out,
Yep.
Down,
down.
down,
Down low or down middle?
down low.
He's
No,
still
no.
okay, guys.
Yeah.
Go up.
Go up
Yeah.
there. I'm already going up.
No, the up left.
Left.
Yeah, but then, oh, I
No,
see
you
there's
still
two-
got 2 paths, you're fine.
Yeah, I still got 2 paths, you're right. So, how about we do this?
Go back to where
Yeah. There you go.
Done so.
As long as you don't burn the last bridge, you're good.
Yeah, that's right. I mean, but I was getting scared because I had cut off a lot of my skin.
Are we allowed to burn bridges in this? Like, is that part of the solution?
Yes,
If
there
we
is.
cross all the bridges, remove this one.
Well, there is a bridge burning part to the list. And then Hamilton cycle here. Yes, there is. If you want to know the theory of Hamilton cycles, the thing is they're almost always possible. You have to have graphs that are fairly constrained before you can't have a Hamilton cycle. And the problem is what's known as an isthmus. You know what an isthmus is in real life?
No.
The country of Panama is an isthmus. It's hard to say.
Oh, that it is, that big wave is separate.
I'm sorry, before they dug a trench across it, Panama was an isthmus. So, like if you have a graph there with some stuff in it, and a graph over here with other stuff in it, and then there's a connection between them that looks like a bridge, that's an isthmus. Now, if you had that, could you make a Hamilton circuit? The problem is, as you went around to visit these things, eventually you've got to leave this bridge and leave this region and go over to the other side, and how are you ever going to get home? You're going to have to recover the parts of the isthmus. So that's the only theory result. This has no isthmus, clearly. It's one big chunk, and you just try. And again, it's about keeping yourself an escape route. But just please remember that this is not going to touch all the edges, just all the nodes. Hamilton circuits touch the nodes once. Euler circuits will touch them often, or a lot of times, because they have to cover every edge. This just has to cover every node. So this is in a way, this is the easier thing. All right, so then let's go back to talking about George Cantor. I have a quick presentation about it.
All of a sudden, oh wait, that's a simple mistake.
Okay, so that's George Cantor, rather late in life. I think he's an interesting but a sad story in a lot of ways. His father was named George also, so that spelling is George without the E on the end. That's a German/Danish thing. Valdemar Cantor. I almost read that as Voldemort.
Yeah.
but I don't think he was like evil or anything. He was a merchant, and he was from Denmark, but he eventually moved to St. Petersburg, where he met George's mom, Maria Anna Bohm. Now, you notice that's a Russian last name? I mean, that's not a Russian last name. Those always end in ski. Not always, but often. Bohm is definitely a German last name. I don't know what she was doing there. But she apparently was quite a musician. And the two of them together were pretty good people, I think. They obviously had a good smoke. George was an amazing artist and musician. Visual art, he was a great painter, but the real thing was his violin playing. He was like concert grade level violinist. And anyway, the whole family had been in St. Petersburg, where the parents met for the first 11 years that George was alive. And then the dad started to, we've talked before about the climate in Russia. The dad started to really suffer under the Russian winters. He was sick all the time and he was falling ill, so they decided to move to someplace warmer. Now, Germany isn't particularly that much warmer, but it's better than St. Petersburg. This is something about I forget who quoted Piaffer here, but they said he remembered his early years in Russia with great nostalgia and never felt at ease in Germany, although he lived there for the rest of his life. And seemingly never wrote in the Russian language, which he must have known. At the age of 11, he would have known to read and write in Russian. He was well educated. But he never did. The sad thing in this story is that he began to have severe depression in later life, mostly in later life. The first bout of it happened when he was in his 40s. That can be a really bad thing. Eventually, he was in and out of, they call them sanitariums in the books, but that's cleaning it up. This sanitarium is usually a place where it's calm and everything is kept very bacteriologically clean, because people have like tuberculosis, for instance, or some other illness that they really need to just settle down and have a calm, clean place to live. But this wasn't that kind of sanitarium. This was a nut house. He was in with all the crazy people, and he was just depressed. He wasn't, raving or anything. So that was not a good environment for him. There's a whole bunch of letters that he wrote to his wife. I mean, he's in his 70s at this point, just begging to be allowed to come home, to leave this crazy place and come home. And they wouldn't. So he died of a heart attack in the sanitarium. That sounds suspicious to me. Anybody who dies, you can say it was heart failure. Right? So who knows what really happened? They call it a heart attack. I don't want to focus too much on that sadness, but let's talk about his work. His biggest thing had to do with the cardinalities of sets. So what do I mean by the cardinalities? If we're talking about finite sets, it's not an issue. We're fine with that. So when I say cardinality of sets, I mean he was the first person to really seriously think about infinite sets and understanding what the sizes of infinity are. So how many different infinities do you think there are?
Infinite amounts.
No, because once something is infinite, isn't that just it? It's as big as you can get. It's to be infinite. Huh? How do you counter that? That's it. I mean, that's a perfectly valid argument. Infinity is infinity. Once you're that huge, how can you get any bigger?
Well, it depends on the rate of which it gets there.
Why does it matter what rate is? I mean, it doesn't matter whether I take infinity and add 1 to it in a second, or I take infinity and add 1 to it in a year. Still, in the end, I've added 1 to infinity, and I haven't changed it. It's like putting a drop into the ocean.
Okay. So now to get your own arguments.
Well, the problem is that just thinking about adding on 1 isn't enough. That you have to think about what Cantor did was say, what exactly do you mean by saying 2 infinities are the same size? What's a precise way to define 2 things having the exact same size? And that's his most important idea is this: the definition of cardinal numbers and saying what it means for 2 sets to have the same size. So, do you recognize these weirdo symbols? the fonts do different things to them, but that is the first letter of the Hebrew alphabet. So that's called Aleph. And he did a lot of lecturing in England, and so, although he was German, but a lot of times the zero, the subscript zero in there, is not read as Aleph zero, but rather Aleph naught, because that's what they say in German. All right. My son was just yelling at me about this. He came across something where in tic-tac-toe in Britain, they call it noughts and crosses. And he was like, how can they call tic-tac-toe something stupid? It's just what they call it, dude. You can calm down.
Like, tic-tac-toe is so eloquent.
I know, really. I kind of like noughts and crosses better, to be honest. But yeah, so get used to that. If I say Aleph naught, I mean the Aleph zero. What that is whatever the smallest infinity is. So what do you think the smallest infinite set is? Half the integers. Just the whole numbers. Yeah. So the cardinality of the natural numbers is defined to be Aleph naught. That's a definition. Now, my making Alephs is going to be really weak. Aleph naught equals the size of the set of natural numbers. Aleph 1 then is whatever the next bigger infinity is. And we still haven't become convinced that there is a bigger infinity yet. So we're going to do that. But we need to see that there's actually a bunch of different sets that have that same cardinality, Aleph naught. Asana, you mentioned the integers. What do you think the cardinality of the integers is? You use the absolute values around a set to mean how many things are in it, right?
It's twice as big as the whole number.
It's twice as big as the whole number, so this is 2 times Aleph naught.
So, her question then, from before, why aren't that just the even numbers, another set of infinity, that's half as big as the natural numbers then?
Right. The problem is, 2 times Aleph naught is the same thing as Aleph naught.
Okay.
Yeah. That's no big. So we can talk. There's a parable about this called Hilbert's Hotel. David Hilbert was a follower of Cantor, and he came up with this explanation. Suppose you've got a hotel that's got an infinite number of rooms, right? And they're all occupied. Somebody's in every room. And now somebody comes in, and you need to find a place for them. What do you do? Well, you get on the loudspeaker system and you ask everybody to please vacate their room and move to the next room down, right? And then, there'll be room for the new guy in the very first room. So after an infinite amount of grumbling, you've got room for one more guy. What if an infinite number of new guests arrive at Hilbert's Hotel? Now what do you do? But you'd have to do that infinitely often. Now you want to make one announcement. Hey everybody, check what room number you're in, double it, and go to that room now, because we're going to make space for some guests. Now all the odd numbered rooms are empty, so put your infinite number of people in them. Yeah. So how we actually see these cardinalities is the real main point of this thing. It's the idea of one-to-one correspondences. 1-1 there, that's not an H. So if you have 2 sets, and you can find a function that goes from one set to the other set that's 1-to-1 and 1-to, that's called a bijection. And that tells you that those 2 sets are the same size. I'm going to use the fancy terminology here. Does everybody know bijection, that word? No, maybe not. So that just means it's 1-to-1 and 1-to. You like the sniper analogy? So 1-to-1 means that each sniper has one target to shoot at, and 1-to means there's enough of the good guys to shoot all the bad guys. Right? If you think about a collection of snipers here and a collection of enemies over here, suppose there's 4 snipers and 5 bad guys. You can have each sniper kill somebody or hit them with paintball, let's say. So it's not so macabre, but if there's more people on this side than there are snipers, this guy runs away. So that's not good. You need to completely obliterate the enemy. Yeah, I'm kidding. I moved the camera so that it would catch the screen, but now we're doing other stuff. Try to readjust. So, well, look, if this guy hadn't been there, this is a 1-to-1 and 1-to mapping. And it looks like a ladder almost, doesn't it? And you know, each one of these guys has one line coming out of it, and each one of the guys on the right has one line coming into it. That's the 1-to-1 part. And there's exactly enough people on the left so that you get arrows on everybody to the right. If this set was smaller, right, if there were more snipers than there were targets, how is that going to look? Let me take one more target of the enemy away. There's only 3 guys over here and 4 of us are shooting. Does this guy not shoot? Well, that's actually not the way functions work. If you have a function, anything in the domain, you have to say what it does. So he's forced to go somewhere. Well, we might as well have him shoot somebody that's already being shot. Okay, that guy gets pierced by 2 paintballs.
That's what I would like.
So what happened there? Because the set on the right here was smaller, we ended up not being 1-to-1. Do you see how that's 2-to-1? So if you have 1-to-1 and you have 1-to, that's projection, and that's what tells you 2 sets have the same cardinality. So let me define a function where it goes from the natural numbers to the integers. That's 1-to-1 and 1-to. I'll tell you that f of, let's call it n, since it's a natural number. I have to do different things in different cases. If n is even, I'm going to do one thing. And if n is odd, I'll do a different thing. It's probably been a while since you've done a piecewise function, but that's what I'm describing here, a piecewise function. You probably saw those in like pre-calculus. So what do we do when n is even? We double it. No. We have it. Because we're talking about a natural number, so if it's even and I cut it in half, I'll have a natural number again. 0 is included in this case, by the way. 0 would be an even number. Right? And where will 0 get sent?
Itself.
To itself. 0/2. Right? Now, what if n is odd? Then I'm going to add 1 first and then divide by 2. And that's not quite enough. That would land me at the same spot as these. I also want a minus sign on that. So what this is, let me try to draw this map for you. On the number line, you get 0, 1, 2, 3, 4, and then compare that to the infinite number line, or the doubly infinite number line that starts at 0 and then has +1 and -1. So +2 and -2. Our mapping sends all these even numbers to the positive axis by cutting them in half. And it sends all the odd numbers off on the other side. No, I don't need to have one. So every even number ends up going to a positive integer, 0 goes to 0, and every odd number ends up going to a negative integer. That's a 1-to-1 and 1-to left. You see that the arrows have one thing that they depart from and one place they arrive? That's 1-to-1. Is it 1-to? Yeah. Everybody in here, you can actually figure out where it came from, what its pre-image was. That is, in other words, you could deduce what's the inverse value. Yeah. So yeah, that's showing that z and n are actually the same size. That's the idea. There's
One's
a
clearly twice as big as the other.
I know, but it's,
No.
but there it is, there's a one-to-one correspondence. So this is how math works, right? Here's the definition of what it means to be the same size. The definition is, I can find a bijection. And you can't argue with the definition, though. So if you accept the definition that a bijection shows two things are the same size, you've got to accept that Z and N are the same size. The thing that's beautiful here is if we're talking about finite sets, that definition absolutely does work. When two sets are the same size and they're finite, then you get a bijection. There's some very strange stuff that comes up as a consequence of this. You know how big the rational numbers are? Well, think about what a rational number consists of. It's probably best to think of it this way. Q is the set of things that look like A over B, where, what do you get? A and B have to be integers.
B can't be 0.
And B can't be 0. But except for that one thing, it's basically, you take a pair of integers and that gives you a rational number. Now there's an equivalence relation there too, like 2 over 3 and 4 over 6 are the same number, right? So there's a little something else we have to worry about. But basically you can think about a pair of integers as a rational number. That means it's like the size of the integers times the size of the integers. So I guess this would be aleph 0 times aleph 0. But guess what? Multiplying infinity by infinity doesn't get you anywhere. That's infinity. That's that infinity anyway. My alephs get weirder and weirder as I go. Just roughly H-shaped things.
What's aleph 1 then?
Well, nobody knows. To this day, nobody knows. Cantor thought that aleph 1 was the infinity of the real numbers. It's called the continuum. And that's actually a great place to stop. He was able to show that the continuum is definitely bigger than aleph 0. So just like the number of points between 0 and 1, bigger than aleph 1. But
So then why is that just defined to be aleph?
well, because we don't know for sure that there isn't some other infinity that's also bigger.
Why can be aleph 2?
This is my favorite quote from him, by the way, before we run off to the quiz. He gave a proof that a 1 by 1 square, that's continuum size, and a line segment of length 1 are the same size. He proved it, and then he wrote to a friend that he didn't even believe his own proof. How can the number of points in a planar region be the same as the number of points along a line segment?